I'm CK. Today we've got another kit from Whadda, used to be called Velleman. This is their DC to Pulse Width Modulator Kit. So it'll take a DC signal, constant DC signal, and break it up into square wave pulses. And that is both useful and could be fun to explore. So we'll put it together, see if we learn interesting things about the circuit, and I hope you enjoy the video. The box, I picked this up from jamco.com, where I get most of my Whadda kits. DC to pulse width modulation. It's a practical gadget because, yeah, sure, you could use this as a DC motor speed control when you're done with it. It's a circuit soldering level 3, which means that they believe it's somewhat complex. And it converts DC voltage into a series of pulses. Makes sense, that's what we said at the beginning. No power loss. There is power loss when you're taking I'm not going to argue with them. Overload and short circuit protection. That'll be nice. We'll see how they're doing that. 8 to 35 volt DC power supply. The last time they told me something could go up to 30 volts, we had magic smoke come out, as you may recall. So I will push this to 35 volts and see. On the back we've got parts, QR code, and the other side just has some regulatory information. Open box. We've got a piece of paper that says go find the online manual, because we're not going to put paper in here, which is I appreciate. Here's the circuit board. Okay, we will need the manual because the component values are not listed on the board, and this one is still printed as Velleman. Velleman is converting all these kits to go under the brand name Whadda because they feel like it. So there's one chip here, there's a frequency, potentiometer here. There's two other potentiometers. I assume one's going to be for voltage and the other one, well, we'll see what the other one is. And one IC and a cup and a big old resistor here, and two other resistors, and we've got loads and a big diode. Maybe that's the one of the protection pieces they were talking about. So let's see what actually are the parts in here. Oh, here's a big old heatsink for the MOSFET that's going to be in there. That's beefy. That's a nice heatsink. I'll scrounge that after I'm done with this kit. Use that for something else. And in here, let me get my scissors. It looks like my top camera is going to run out of battery any second, so I'll kind of scoot through this. Got some resistors and diodes. Actually, there's not. Oh, there's the big diode. Wow. That's beefy. Then we've got 3 5-watt resistors. Dissipate a lot of heat. Here's the IC that's going to control things. It's a SG3525AN. I'll look that up. Some caps, decoupling caps probably. Screw posts for wire. Here's our MOSFET, which will do all the switching. AFP 5205. And a couple of electrolytics, one big one medium-sized one, and the trimmers, and one, I don't know if this is transistor or voltage regulator. Oh, it's transistor. So that's the bits and pieces. Now I'll get the soldering iron heated up, and we'll put this thing together. Pulled up the build guide, and it's typical Velleman, pretty good. All drawings, no photos. Well, actually there is one photo at the very top of the finished unit. So what we're going to do first, they would like us, and we'll approach it this way because we're fine with that. We're going to do the 3 standard diodes first, the 4148s and the 4007. So the 4148s go in D1 and D2, and they are, of course, polarized. So when we look at, why am I missing my pointy thing again? When we look at D1, we can see there's a heavy white line, D2 heavy white line, D3 heavy white line going the other way. And those heavy white lines are where we will match the black stripe or the silver stripe on the diodes themselves. And note that the 4148 diodes have their stripe on this side. The D3, the 4007, which is the power conditioning diode, or power protection diode, whatever you want to call it, stripe goes the other way. And we won't solder that quite yet. Now we're going to put the IC socket on. I didn't look up the IC socket, the IC number yet. I will here momentarily. I'm going to set the socket on my pinky finger behind the board, and then do one leg. Let it cool. Take a look. Everything is all flat and useful. Actually, I'm going to look up this chip anyway. It's a SG3525. Data sheet, and that is a pulse width modulator control circuit. Well, there you go. So everything is going on to do the modulation in this chip. And this is apparently Motorola originally designed it. Let's see sorry, there's a security code here to get at the actual data sheet, I guess, to prevent bots. And this is not by Motorola. That's an emblem I don't recognize, but that's okay. I'm going to go ahead and solder all the connections I've got right now, and you notice this is a simple board. I didn't even look at the front. All the traces are on the back, so it's single layer, not through-hole plated, just regular copper. Now PCB pins, we've got, oh I see, we're going to put pin in VREF. Where is it? I didn't clip those leads yet, I will. So we'll put VREF here. It's a little stainless steel peg. Oops, and it of course fell out when I flipped the board over. I think that may be so you could sense from an external display or something like that, maybe another component you care about if you're making motor control or anything that needs pulse width modulation. Heck, you could make a audio oscillator if you really wanted to be crazy about it. Now we'll do all the resistors. Let's see, there's two 20s right there, red, red, brown. 2K20 right there. And we've got a 10K and a 100K. And then a 224, because you can see the yellow there. And then we've got an extra one. I think that's a 47K. I don't know. Yeah, it's 47K. I don't know what it's for though, because they don't list a 47K anywhere. I'll look ahead a little bit just to make sure. Huh. I don't know. So we'll put the resistors on the board, not much more to say about them. So I will not comment for a little bit and speed up the playback probably. And there's all the resistors on the board. Now we'll put all the trim pots. There's two 10K and there's one 250. Let's see where the markings are. No, seriously guys, where are these marked? I can't see a value marking on these. I really can't. This is unusual. They're out of Spain. They're Fire, P-H-E-R. Okay, this one is imprinted as 220K, is that right? It's supposed to be 250K. Look here. Oh, there's very faded marking on here. These are 10Ks. Okay. It's very hard to see the markings, but these are the two 10Ks, and this is what's listed as 250, but the marking on the board shows 220. Not going to make much of a difference. Just interesting to note. And again, all that does is just limit the range it can be at, which is not a big deal. Why is there... Oh, they've got different holes available, I guess for different parts. Yeah, they've got a very small one and a very short one. Oh, I see. Sometimes they must put in some of those square or rectangular ones, you know, the blue ones that you see with the little screw on top. I think they may sometimes ship with that. Now we'll do the ceramic caps. They're all 104s. And as I do, I just clip them out of the cardboard. I don't try and pull them out because you'll just get frustrated and you'll bend pins, and just better to cut them out. And these are, of course, not polarized. They can go in either orientation. That'll be in C1. Now we'll put our transistor on. Same thing, cut it out of the paper. It's tucked way in here, so we'll bend the middle pin back a little bit. Make sure the flat side of the transistor is facing the flat outline on the circuit board. Then we'll put the electrolytic caps on, and they are polarized. Long lead is positive, short lead and the white stripe is negative, and there's a positive plus sign on the circuit board. Put the big 100 microfarad here. Then we've got two, I think they're 10s. Yeah, they're 10s. One gets tucked away in here. It's a very densely packed board. Not a problem, just something to comment on. And now we put the big old diode in. This feels like it's protecting us from backflow from the load. If it's a motor or big old coil, the inductance, release of inductance can, oh man, those leads are really thick. I'll solder these in place now. So with these really thick leads, I'm going to grab some more solder. With these really thick leads, you're going to want to linger a little bit longer with your soldering iron to make sure it gets hot enough for the solder to fully, see it, I don't know if you can see this, it's haloing there. Just closed up the circle around the lead. The lead's got to be warm enough for the solder to flow around it so you get a good connection. Now we're going to put our screw terminals on. And we've got 3 of them. We've got one here at J1, one at J2, and one at J3. And just make sure you've got the place where you put the wires in facing the correct direction, or else you'll go to hook up wire later and you'll say, oh no, I put it in backwards. I have to take them back out. Now we'll put the big old resistors on. They're all the same. And this is why when they say, no, on the box it says, no power loss. Well, I'm sorry, if you've got these big old 5-watt resistors that are going to be radiating heat, that's called power loss. These two go vertically. I mean, anytime you have a resistor in a circuit, you are going to have a little bit of power loss, because that's kind of what the resistor is doing when it's giving off heat. It's converting electrical energy to heat, and that means you're losing that electrical energy. And now we're going to put the transistor and the heat sinks on, or heat sink on, and we've got a couple of screws to hold it onto the board that go kind of in these gaps here, and then a screw that will mount it to the board. So we're going to do that first, but what I'm also going to do, I brought over my thermal paste, a little tube of thermal paste, and I'm going to put some on here because that just helps. I dolloped too much out. That will help the heat transfer to the heat sink better. You don't have to do that, but if you were going to use this actually in a actual product, you would definitely want to put some thermal paste on here, particularly if you're going to be operating at the higher end the 35 volts or whatever, because this thing is going to dissipate a good bunch. It's going to be doing a lot of switching, depending on the frequency, switching of reasonably higher voltages, and that thermal paste will help dissipate that again. So I'm going to drop this screw in and put the lock washer and nut on. And I am going to be not tightening it all the way, just going to be tightening it snug, but not too snug, because we have to get it aligned with the holes and get the heatsink screwed down, and you want to make sure you do that before you tighten this down very much, or before you solder the connections. And again, as you can see, there's a heavy white line there. That's the side where the heatsink on the chip goes, the aluminum plate on the back, and these pins got a little cattywampus, so I'm spreading them back out. Okay, we've got that in place for the moment. Now we'll put these two self-tapping screws in here, or we'll let them roll across the workbench, whatever works. Now we can screw the transistor down to the heatsink. We do want to get that kind of tight so there's as much surface area between the transistor and the heatsink as we can get. Now we will put the IC in, bending the IC leads a little bit inward against the side of my workbench, and then there's a notch on the IC that we want to match with the notch printed on the circuit board and the socket. And there we go. So that's the way it looks when it's been built. And now I'm going to go get my bench power supply and some wire, and we'll give this thing a go. Okay, we're set up, and as you can see, I've got the oscilloscope set up so we can look at the pulse width and voltage as we go along. Now, the input voltage goes into this pin and this pin. Output voltage comes out from this pin and this pin. This is to set up an external voltage control modulator. It looks like they actually have a kit. It might be Velleman K8000 that I'll take a look at and see what we can see if I can find that, and then I'll build that and use this with it. But for right now, we've got our power supply hooked up, and we're going to increase the voltage. And as you can see, the motor starts to turn, and if you look at the scope traces, I'm going to have to adjust this a little bit. You can see the pulse, it's about coming out at about 5 volts right now. I'm going to change the frequency on that, if I can get my screwdriver positioned correctly. As you can see, I'm increasing the frequency of those pulses, and you may not be able to hear it, but the motor has sped up. Now, I believe this one will do pulse width. Yeah. Oops. Guess it's maxed out. Man, I should have nailed this down. So that's the pulse wide, I guess. Going the other way, and it's not actually changing the pulse width. That's interesting. I thought it would. Let me give it a little more voltage. So that's now, how many volts is that? That's like, oh gosh, that went up to 20 volts peak to peak. I don't want that. Let me come back a little bit more. 12 volts peak to peak. And again, frequency adjusts here. So it looks like we're not varying the pulse width with any of these things. We're varying the frequency of the pulses. If I back this one off, I don't even know what this actual rheostat does. But that's what it's doing. We can put out a lot of voltage. Again, I'm giving it 8.99 volts in, and we're showing 20 volts out. Now let me speed this up a lot, see if we can burn anything out. I don't want to burn out this motor particularly, but look at that. You can see how now at top frequency it's almost one solid line. So the pulses almost merge. So that's what we're doing. It's not the cleanest power signal I've ever seen in my life, that's for sure. We've got these opening peaks that are quite high. Now I'm going to do something a little different, or a little more. Back in the voltage back off. I'm going to increase the input voltage, because again, it says it can take up to 35 volts. I've got this voltage limited to 30 volts. Let me change the voltage limit. Oh, my power supply will only go up to 32. So that's about 32 volts, and we're still, we're getting that as the output, so I may be burning out my motor. I don't want to do that. So that's the way it works, and as you can see, they've got the connections here so you can control the voltage externally with another unit, and you can sense it from this pin, or I think you can sense it directly here. I'm not certain. I'll have to look at that when I get the other kit. But that's it. That's a pretty neat unit. Went together pretty quickly. And I think you can use it in a lot of things. You could use it on a train set. You could use it on a light. You could use it on a motor, as I'm doing. It did come with one extra 4.7. Is that a 4.7? Yeah, 4.7K resistor. That's not needed for anything, even though I could probably self-control it with that, but I'm not going to bother doing that. All in all, a useful, good kit from Whadda, and I hope you enjoyed the video.